Hi everyone, today I want to talk about producing parity plots in the context of catalysis. So context of catalysis. Now, when you come across literature, you might see something like this, where you have the theoretical data plotted against experimental data. And usually if the plots are well done, they will follow a trend like this, and you'll have a case of y equals x. Now this is what people usually use to show that their model is a valid model, so that if you have some experimental data and you have a mathematical model, and you have a mathematical model, it will make very good predictions. So let's say you have a real size reactor in the lab. Okay, so this experimental data you get from the reactor in the lab. So you put in your reactants, the appropriate reactor conditions, the residence time, everything. You put this into let's say the real reactor in the lab, you will get experimental data. And usually, what's this kind of experimental data? Sometimes it's the conversion, sometimes it's selectivity, sometimes it's even the, I don't know how to do this Greek letter, the extent of reaction. But of course, for this video, we want to keep it simple. We look at conversion first and foremost. Okay, so usually there'll be all this data that's being captured by analyzing the products from the reactor in the lab, and then you will get the experimental data of the conversion and selectivity. Now, how then would you produce, just ignore this side, just ignore this side, across this line, ignore. How would you produce all these theoretical data plots then? Well, whatever you are doing in your lab to produce the experimental data, you need to simulate it in a computer. You need to simulate a reactor in a computer. It's a computer, so that when I know the conditions of my reactants, which I simulate again, and then I know my conditions like temperature, pressure, and everything into this simulated reactor, I will get the same conversion, selectivity, and etc. So that's the thing about producing a parity plot, and that will actually show that the model that you are doing. So let's say you have a particular catalyst model which you place into this simulated reactor, and if you get the appropriate conversion and selectivity, that will mean that your theoretical data will predict your experimental data pretty well, so that you will get this one straight line showing y equals to x. And that's the ideal, of course. Now the question is, how then would you go about doing this simulated reactor in the computer that tries to emulate what goes on in the lab scenario? Now that's the really tricky part, which I want to go on elaborating more about in this video. So to do your simulated reactor, so let's say you have the lab reactor again, and we know why we want to do a simulated reactor, to generate that parity plot. So in a real lab, of course, you have the real T, P, and the reactants, and then you'll get some products. In the simulated reactor, you also input some value of TP and reactants. Of course, it's not a real temperature or pressure, it's just a number you key into your Excel, HYSYS or DWSIM file, whatever software you're using. And then there will be some mathematical model, some FX that will churn out a value of conversion and selectivity. And of course, from these products, you will also have the real experimental conversion and selectivity. And then what this model produces is the theoretical. This is what we explained earlier. So question is, what is this FX made of? Okay, I mean the experimental ones are obvious, but let's look at FX. This FX I'm talking about. Now, it's not strictly speaking, they don't call it FX in the literature, but I mean for simplicity's sake, we just call it like some kind of a mathematical function. And what would be in this mathematical function? Okay, so it depends on, of course, on your lab reactor, because if this is a CSTR, then this function here will be a characteristic of a CSTR. If this is a PFR, then this function will be characteristic of a PFR. Okay, so let's say you have a CSTR scenario. Let's say in your lab you have a CSTR that's running. Let me draw a stirrer here. You have a CSTR that's running with some catalyst inside. Then what would you need to do? You need to look at the mass balance of the CSTR equations. That will give you this very familiar V equals to FA naught X over RA equation. This is actually mass balance over CSTR. CSTR. And of course, if you have a catalyst model, you plug it in here. So the catalyst model will help you to determine the rate of the rate of reaction. Well, that's pretty straightforward enough. And of course, for this mathematical model, so this is what we are doing here in this FX. Okay, this here is this simulated reactor. So this is of course not a real CSTR. This is a mathematical model of a CSTR, the mass balance impact. So yeah, so for that you need to input the catalyst model, which is what you can see online. Let's say using for the methanol case, you can see Graf and Skurzypek, very common names in literature. Graf and Skurzypek's model, and there are lots of other models as well. And what you have if you have a CSTR, of course, if you want to simulate a CSTR in a computer, then you want to look at the volume of this lab reactor, and you kind of plug it in here, and you look at the flow rate of this lab reactor. So you try to simulate everything that's going on in the lab, and then you try to plug the numbers in, and hopefully, if everything goes well, this X is which is the theoretical conversion. Alright, this X, the theoretical conversion, will match up well with the experimental conversion. So to generate the parity plot for a given set of inputs into for a given set of inputs, that means let's say you have this reaction, reactor input. Let's just call this whole thing reactor input, which is your TP, flow rate, all the compositions and everything. So for a given reactor input, you will get some experimental reactor output. So you simulate this in that reactor for the same given reactor input. If your reactor output churned out by the model is very similar to this, then you will have a beautiful parity plot. Now, of course, the very important trick is to get the reactor model right. So if it's a CSTR, we do a CSTR model. If it's a PFR, we will do a PFR model. So PFR model, it's the differential form, I believe. dV equals to minus FA naught dx over RA. So this is the PFR version. I'm sorry about the writing. Okay, let me write it again. The dV equals minus FA naught dx over RA. Okay, so this is the PFR version. Sometimes it's used for the catalyst case, they call it the packed bed reactor. I mean, it's a pseudo PFR. The mathematical model is the same, but it doesn't mean that the real packed bed reactor is like a PFR. I mean, it can be mathematically similar given some simplifying assumptions. So we kind of use the PFR model. And of course the CSTR, if it's mixed with catalyst, sometimes it's called the spinning basket reactor. I'll just call it SBR. But in essence, the model we use is a CSTR model, which is something like this. Now, of course, if you want to produce a proper parity plot, you will need the reactor model. This is just an overview. Proper parity plot. You need a proper reactor model, a proper catalyst model, and of course you will also need a thermodynamic model. Now, of course, you know why we need the reactor model. The reactor model will link the catalyst model plus the whatever reactor inputs. It will churn out an X value, let's say a conversion value. So these two are quite easy to understand. Now, why do you need a thermodynamic model? Why do you need a thermodynamic model? Well, let's say your catalyst model depends on partial pressures or fugacities. Well, the thermodynamic model will help you to determine what these fugacities or partial pressures are, based on the feed input. And of course, the thermodynamic model will also help you a lot in the CSTR equations. Because, not CSTR equations, the PFR equations. Because the density of the stream is always changing, then your mass balance will be always changing because the volumetric flow rate again is changing all the time. So, for the PFR, we will need, you can kind of guess it's kind of a lot more complicated, but this is just an overview of how you generate a parity plot. You need this model, this reactor model, and this reactor model will need the catalyst model and the thermodynamic model also. So this reactor model I'm talking about is the mass and energy balance of the mass and energy balance of the reactor. This is what I'm talking about. Okay. So mass and energy balance of the reactor, you need the thermodynamics and you need the catalyst as well. This is the kinetics model. So this is the overview of how you generate a proper parity plot. Hope this helps to clarify some concepts. And if nothing else, if any questions, please post in comments. And if nothing else, I'll see you guys next time. Bye.